Hello everyone. In this video we're going to talk about chemical reactions and chemical reactions are basically what occurs when bonds break and new bonds form. They're not super complicated, at least we're not going to get into super complicated ones, but we are going to have to figure out what's happening. Okay, so we break bonds in reactants and we form new things to make new products. We break bonds initially and then we reform bonds to make new things. The bonds are ionic or covalent bonds, just like we got done studying. Reactants and products, so the reactants are the things we start with. Products are the things we end with. So reactants react to produce products. Reactants react. They produce products. Okay? Students will often mess up these terms. Just think about what they mean. Products are produced. That's what we end with. Reactants will react. That's what we start with. These two things are going to be different. That's what makes a chemical reaction a chemical reaction. Because we're making and breaking bonds, valence electrons are involved in these reactions. Okay? So here's an example of a reaction. We have hydrogen over here. We have oxygen right here. These are our reactants. Okay? So hydrogen is a reactant and oxygen is a reactant. Our product is water over here, H2O. Now if you look at what this says, it says hydrogen, which is going to be hydrogen single bonded to another hydrogen, reacts with oxygen, which is oxygen reacting or double bonded to another oxygen, produces, oh, and this little 2 out front, that says I actually have 2 of these H2 molecules, produces water, H2O, but it actually produces 2 of these things. Okay? So how did this get from double bonded or 2 single bonded hydrogen molecules to this thing? Well, what has to happen is these bonds right here have to break. So instead of having hydrogen as a molecule, I have hydrogen with its electron and hydrogen with its electron and hydrogen with its electron and hydrogen with its electron. So we have to break these bonds apart so this thing is floating around. And then these bonds also have to come apart. So now I also have oxygen with its 6 valence electrons and oxygen with its 6 valence electrons. And then that gives a chance for these new bonds to form. Okay, so oxygen will share, and so we went from having 4 hydrogens and 2 oxygens to having 4 hydrogens and 2 oxygens, but in a completely different arrangement, in completely different bonds, and a completely new substance. Okay, so that's a reaction. You actually, this reaction has been done. You burn hydrogen with oxygen, and it produces water. It's actually very violent, creates a pretty big explosion when that happens. Another one is the reaction of iron with oxygen to produce iron oxide. Commonly, this is rust. Okay? So you're starting with shiny silver iron, you're reacting it with the gas, which is this oxygen, and you're producing this brown crumbly stuff, which is not really metallic, it's ionic, it's rust. Okay, so we got something new out of this reaction. The oxygen bonds broke apart, the iron transferred electrons to those oxygens, and then they stick together. Okay. Now, in a chemical reaction, you cannot create or destroy mass. Okay, so remember, we have laws of conservation of energy, which says the total amount of energy stays the same. It's not created or destroyed. It's not gained or lost. It just changes forms. Well, the law of conservation of mass says the same thing. Atoms, that is the same mass, cannot be created or destroyed in a regular chemical reaction. There is this weird nuclear reaction where we can actually change mass into energy. We're not going to get into that much, at least not in this unit. So the amount of matter, the amount of mass, the total number of atoms cannot change in a reaction. All that changes is how they're bonded together. So the mass before the reaction occurs is the same as the mass after the reaction occurs. And it's more than that. If we go back to this hydrogen, H2, when we had 2 of those, plus oxygen, O2, produces 2 H2Os. Okay. Not only do I have hydrogen and oxygen at the beginning and hydrogen and oxygen at the end, I have the same number of each. This says 2 H2s. That's 4 hydrogen atoms. Okay. 4 H's. Over here, I have 4 H's, 2 water molecules. Each of those water molecules has 4 hydrogens. So there's 4 hydrogen here. Okay. This says 2 oxygen. I have 2 oxygen atoms. This says 2 H2Os. That says there's 2 oxygens. So not only does the total amount of atoms not change, but the total amount of each type of atom stays the same. So if I start with 4 hydrogen atoms, I end with 4 hydrogen atoms. I started with the element hydrogen. I end with the compound water. Okay, so just because I have the same atoms doesn't mean I have the same compounds, because I have new bonds, old bonds broke, new bonds formed, we have a completely new compound. Okay, now in a chemical change we have, or in a chemical reaction we have chemical changes. So we need to juxtapose that with a physical change. So a physical change is when you change matter without changing its identity. So you start and end with the same thing. If you think about taking a board and cutting it in half, you started with a board, you ended with a board. You didn't change anything about it except its length. Okay, if you sharpen your pencil, you haven't changed anything about it except its length. You changed its shape, but you didn't change what it's made out of. It's a physical change. Okay, you have the same thing at the beginning and at the end. Phase changes are often confused for chemical changes, but they're not. Okay, if you take a cube of ice, ice is solid water, water in the solid state. So you have hydrogen and oxygen bonded together in water molecules, and as a solid, these things are just all packed together in a nice orderly arrangement. When you melt them, they're just free to move around more. You haven't created a new substance, you just let it move. And when you turn it into a gas, they move around even more, but they're still individual molecules of hydrogen and oxygen stuck together. There's nothing new there. So a phase change is a physical change. You start and end with the same thing. You have maybe hotter or colder water, but you still have water, or hotter or colder, whatever substance you're heating up or cooling down, but it's still the same thing. Okay? A chemical reaction, on the other hand, changes stuff into new materials. So we've looked at a couple different chemical reactions. We saw that combining hydrogen and oxygen gases, you're going to end with water even though you started with 2 gases. So you have different materials at the beginning and at the end. That's the key to look for in a chemical reaction. If you ended with something new that you did not have before, a chemical reaction occurred. And there's some physical properties that you can observe without changing matter. So you can observe something's mass without changing what you have. You can observe something's temperature without changing what you have. You can measure something's density without changing what you have. Those are all physical properties. If you want to know about a chemical property like reactivity, you actually have to carry out a reaction, and it's going to change the matter. Okay? So what are some signs? What are some indications we can look for that a reaction has occurred? Well, you guys saw in a lab that when you mixed a couple of the chemicals together, different things happened. Okay, so you got new materials that didn't exist before. Rust is an example of that, but also in a lab, you guys mixed 2 chemicals together and it turned white and chunky. It sort of looked like maybe spit or snot or something in the dish that wasn't there before. You put 2 clear liquids in and out popped this white floaty stuff. That's something new. Okay, that wasn't there before. You also mixed 2 chemicals together and you got bubbles in it. It started fizzing a little bit. That gas particle, that bubble, that's something new. So those are both things to look for. Okay, if gas is forming, this is not due to boiling, but simply because bubbles are being produced. Like if you've ever taken vinegar and baking soda and mixed them together, it fizzes. Okay, that's an indication that a chemical reaction is occurring. If you have something that you mix together and the temperature changes, that's an indication that a chemical reaction can be occurring. If the color changes, so think about rust. Okay, iron is gray, rust is brown. Copper is shiny and copper colored, reddish brown. Copper will react and form a green substance, right? That's something new and different. It gets a color change in it. Now you can also heat up a metal and it'll start glowing red. That's not a chemical reaction. That's a color change because you made it warmer. That's a physical change. But if you react lead nitrate, which is clear, with potassium iodide, you can get lead iodide, which is bright yellow. So you can get some cool color changes that occur. And these particles that formed, that's called a precipitate. Okay? That's when you mix 2 liquids together and you get a solid that forms. Okay? And milk spoiling is actually a chemical reaction. It changes into something else. It gets all chunky and gross. Okay? All right. There are some things you can do to speed up chemical reactions. Or slow them down even, okay? Because in a reaction you have to break old bonds and form new ones, so the particles have to collide with enough energy to break their old bonds and form new bonds, okay? So to speed up a reaction, you're either going to have to increase the number of collisions or add energy so they hit harder and more often, Okay, so you can increase the temperature. Remember, that makes the particles move faster. That means they're going to collide more often with more energy, so you get reactions to happen faster. Okay. You can increase the concentration, which is how much stuff is in there. If you add more reactants, they're going to hit more often. It's like if 3 people are on an elevator, they can all fit in there comfortably and nobody touches. If you cram 30 people into an elevator, nobody's happy because everybody's touching each other. You increase the concentration, you increase the reactions. Okay. The surface area. Now, if you think about this, basically it's saying if there's more places for a reaction to occur, it's going to happen faster. So if you have a big giant lump of something, okay, the only place the reaction can occur is on the outside. If you cut that lump in half, you've exposed 2 more surfaces for the reaction to occur. So if you cut it in half, there's more surfaces. And if you cut it in half, there's more surfaces. So if you have lots of little pieces, that will react faster than one big piece. Okay? Stirring, again, that's going to add energy. It's going to make them collide more often. It's going to speed it up. And then you can actually add a catalyst, which is something that speeds up a reaction without changing the reaction. It's a chemical that helps the reaction occur. There's the opposite of a catalyst called an inhibitor, and it gets in the way of a reaction and slows it down. Now, you might be asking, okay, reactions happen. Why do we care? Reactions happen every day, all the time, and they're a very big deal. Okay, we depend on them. Okay, we've talked about how energy changes in a chemical change. Okay, well, you're actually doing cell respiration. You eat food, and chemical reactions allow you to get the energy out of that food. Cell respiration is a chemical reaction. Plants are doing chemical reactions. They're taking in energy from the sun, carbon dioxide, and water to build up glucose and polymers of glucose and make themselves. Okay, so chemical reactions make life possible. Okay? If you've ever driven a car, burning fuel is a chemical reaction. Okay? And making fuel requires chemical reactions. There's a thing called a catalytic converter that it actually heats up the exhaust and reacts it into some other products to make it less harmful to the environment. It actually depends on a catalyst. If you think about catalytic, it uses a catalyst to help a reaction occur more completely. The catalyst it uses is platinum, actually, which is pretty expensive. Your electronics, so the iPad you're watching this on, it depends on chemical reactions. The battery in it that makes it work, the chips, the computer chips that make it work, they depend on reactions in order to produce them, in order to make them. Things that you use every day, plastics, soaps, medicines, these are all made with chemical reactions trying to make our world better. So chemists actually have done lots and lots of things, learned lots about how matter works and how to make stuff better. Imagine living in a world without plastic. Take away everything that you have that's plastic and see what's left. We take this for granted, but it's a fairly new polymer for us. Synthetic rubber is another big one, another polymer that we use. Just everything around you depends on chemical reactions to produce them, to make it, to take one thing, turn it into something else that we want in order to make our life easier to do, more beneficial, to get more information, to make our lives better. Chemistry, chemical reactions allows that to happen.